At first, the object called 3I, Atlas seemed to follow the familiar script of an interstellar visitor. It arrived from deep space, curved around the sun, dimmed as it moved outward, and appeared ready to vanish back into the darkness between stars. That pattern alone wouldn't have raised eyebrows. The problem began when astronomers tightened their calculations. As the uncertainties shrank, the trajectory stopped looking ordinary. Atlas wasn't simply leaving the solar system. Instead, it was drifting through one of the most precarious gravitational environments that exists, a region where even tiny forces can permanently alter an object's fate. As it moves outward, Atlas's projected path takes it extremely close to Jupiter's Hill sphere, the zone where Jupiter's gravity competes with the Sun's. This isn't a sharp boundary but a fragile transition, and Atlas isn't passing comfortably clear of it. It comes close enough that a minuscule change in speed or direction could mean the difference between permanent escape and long-term entanglement. That near miss is what unsettled researchers. If the object had passed well outside this region, there would be no mystery. But grazing a gravitational tipping point like this places Atlas in a regime where motion becomes chaotic and outcomes diverge dramatically. In such places, gravity behaves less like a smooth curve and more like a razor's edge. Jupiter plays an outsized role here. Its gravity can steal energy from passing objects or donate it, reshaping trajectories with remarkable efficiency. Under the right conditions, a flyby can redirect an object's future entirely, even setting it up for a return to the inner solar system. Normally, this would be dismissed immediately. Natural objects don't plan encounters. Comets and asteroids don't fine-tune flybys. They simply respond to gravity and move on. But Atlas has already shown behavior that doesn't fit comfortably within that expectation, which is why some researchers shifted the question. Instead of asking whether such a scenario is likely, they asked whether it is allowed by physics at all. When the problem is stripped of science fiction assumptions, it becomes a matter of extreme engineering rather than impossible laws. Atlas is moving at tens of kilometers per second relative to the Sun. Altering that motion significantly would require shedding enormous amounts of energy. Chemical propulsion is useless at that scale, and even ion propulsion struggles once mass increases beyond small spacecraft. Only plasma-based concepts begin to approach feasibility. In theory, accelerating charged particles to very high velocities dramatically improves efficiency. The true bottleneck becomes power. Sustaining such systems would demand energy far beyond current human capabilities, but still within the bounds of known physics. Then an alternative idea changes the picture entirely. What if Atlas was never meant to maneuver itself? What if its purpose is to release something much smaller as it passes through Jupiter's gravitational influence? Reducing the velocity of a payload weighing only a few tons remains difficult, but no longer absurd. Techniques involving magnetic structures interacting with plasma or solar wind suddenly become relevant. In that case, the energy source doesn't have to be onboard the smaller object. It could be provided by the larger system during deployment. Seen through that lens, some of Atlas's strangest features become harder to ignore. Its persistent anti-tail, composed of energetic particles moving counter to the solar wind, could simply be a natural oddity. But it could also act as a vast interaction surface, exchanging momentum with surrounding plasma and harvesting energy at scale. Even low efficiency would yield enormous power given the environment involved. Timing adds another layer. Atlas has already passed close to Venus, Mars, and now Jupiter, all planets of scientific importance. Earth is the notable exception. A carefully tuned interaction with Jupiter could set the stage for a future return under far more favorable conditions. None of this proves anything extraordinary. Natural explanations may still emerge. But what matters is that none of these possibilities violate known physics. They demand technology far beyond ours, but not imaginary technology. Even if Atlas turns out to be entirely natural, its behavior already places it among the strangest interstellar objects ever observed. Near Jupiter's gravitational frontier, motion becomes unforgiving. Differences of mere meters per second can decide whether an object escapes forever or remains bound for decades. Most interstellar visitors never come close to this kind of instability. They sweep through and are gone. Atlas is doing something else entirely. It is threading a region where precision suddenly matters. In such environments, uncertainty becomes dangerous. Mission designers avoid them unless they have a reason, because small errors grow rapidly while small corrections can be incredibly powerful. For a natural object, this precision would be meaningless luck. For an engineered scenario, it would be the entire point. Once the possibility of releasing a smaller payload is considered, the puzzle rearranges itself. The main body wouldn't need dramatic maneuvers. Its role would simply be access. Near Jupiter's sphere of influence, modest adjustments on a small object could lead to long-term stability in regions where gravitational forces balance.